This screen behind me is connected up to the camera that's filming me. But the camera in turn is filming me with the screen. This creates a loop with multiple copies of me appearing on the screen.
This is a classic example of a feedback loop. We get a picture in a picture in a picture. At first it seems fairly predictable, but as we zoom the camera in, some pretty strange things begin to happen. The first thing I notice is that the object I'm filming stops bearing much resemblance to what now appears on the screen. Small changes in the movement of the match become rapidly amplified as they loop round from the camera to the screen and back to the camera. So even though I can describe each step in the process mathematically, I still have no way of predicting how tiny changes in the flickering of the flame will end up in the final image. This is the butterfly effect in action. But now here comes the spooky bit. With just a slight tweak to the system, these strange and rather beautiful patterns begin to emerge. The same system, one that's based on simple rules with feedback, produces chaos and order.
The same mathematics is generating chaotic behaviour and patterned behaviour.
From the 70s on, more and more scientists began to embrace the concept that chaos and pattern are built into nature's most basic rules.
Take this pebble. Is it a sphere or a cube? Or maybe a bit of both? And what about something much bigger? Look at the arch behind me. From a distance, it looks like a semicircle. But up close, we see that it's bent and crooked. So what shape is it?
Mandelbrot asked if there's something unique that defines all the varied shapes in nature. Do the fluffy surfaces of clouds, the branches in trees and rivers, the crinkled edges of shorelines share a common mathematical feature? Well, they do. Underlying nearly all the shapes in the natural world is a mathematical principle known as self-similarity. This describes anything in which the same shape is repeated over and over again at smaller and smaller scales. A great example are the branches of trees. They fork and fork again, repeating that simple process over and over at smaller and smaller scales. The same branching principle applies in the structure of our lungs and the way our blood vessels are distributed throughout our bodies. It even describes how rivers split into ever smaller streams. And nature can repeat all sorts of shapes in this way. Look at this Romanesco broccoli. Its overall structure is made up of a series of repeating cones at smaller and smaller scales. Mandelbrot realized self-similarity was the basis of an entirely new kind of geometry, and he even gave it a name: fractal.
Now that's a pretty neat observation. But what if you could represent this property of nature in mathematics? What if you could capture its essence to draw a picture? What would that picture look like? Could you use a simple set of mathematical rules to draw an image that didn't look man-made?
The answer would come from Mandelbrot, who had taken a job at IBM in the late 1950s to gain access to its incredible computing power and pursue his obsession with the mathematics of nature. Armed with a new breed of supercomputer, he began investigating a rather curious and strangely simple-looking equation that could be used to draw a very unusual shape.
What I'm about to show you is one of the most remarkable mathematical images ever discovered. Epic doesn't really do it justice. This is the Mandelbrot set. It's been called the thumbprint of God, And when we begin to explore it, you'll understand why.
Just as with the tree or the broccoli, the closer you study this picture, the more detail you see. Each shape within the set contains an infinite number of smaller shapes, baby Mandelbrots that go on forever. Yet all this complexity stems from just one incredibly simple equation. This equation has a very important property. It feeds back on itself. Like a video loop, each output becomes the input for the next go. This feedback means that an incredibly simple mathematical equation can produce a picture of infinite complexity. The really fascinating thing is that the Mandelbrot set isn't just a bizarre mathematical quirk. Its fractal property of being similar at all scales mirrors a fundamental ordering principle in nature.
When we look at complexities in nature, we tend to ask, where do they come from? There is something in our heads that says complexity does not arise out of simplicity. It must arise from something complicated. We conserve complexity. But what the mathematics in this whole area is telling us is that very simple rules naturally give rise to very complex objects. And so if you look at the object, it looks complex. And you think about the rule that generates it, it's simple. So the same thing is both complex and simple from two different points of view.
Complex systems can be based on simple rules. That's the big revelation. And it's an astonishing idea. It seems to apply all over our world. Look at a flock of birds. Each bird obeys very simple rules, but the flock as a whole does incredibly complicated things, avoiding obstacles, navigating the planet with no single leader or even conscious plan. But amazing though this flock's behavior is, it's impossible to predict how it will behave. It never repeats exactly what it does, even in seemingly identical circumstances. It's just like the Belousov reaction. Each time you run it, the patterns produced are slightly different. They may look similar, but they are never identical. The same is true of video loops and sand dunes. We know they'll produce a certain kind of pattern, but we can't predict the exact shapes. The big question is, can nature's ability to turn simplicity into complexity in this mysterious and unpredictable way explain why life exists? Can it explain how a universe full of simple dust can turn into human beings? How inanimate matter can spawn intelligence?
At first, you might think that this is beyond the remit of science. If nature's rules are really unpredictable, should we simply give up? Absolutely not. In fact, quite the opposite.
Fittingly, the answer to this problem lies in the natural world. All around us, there exists a process that engineers these unpredictable, complex systems and hones them to perform almost miraculous tasks. The process is called evolution. Everywhere you look, you can see evolution using nature's self-organizing patterns. Our hearts use Belousov-type reactions to regulate how they beat. Our blood vessels are organized like fractals. Even our brain cells interact according to simple rules. The way evolution refines and enriches complex systems is one of the most intriguing ideas in recent science.
My interest in my PhD research in complex systems was to see how complex systems interact with evolution. So on the one hand, you have systems that almost organize themselves as complex systems, so they exhibit order that you wouldn't expect. But on the other hand, you still have to have evolution interact with that to create something that is truly adapted to the environment.
Evolution's mindless yet creative power to develop and shape complex systems is indeed incredible. But it operates on a cosmic timescale. From the first life on Earth to us walking about took in the region of 3.5 billion years. But we now have in our hands a device that can mimic this process on a much shorter timescale. What is the invention I'm talking about? Well, there's a good chance you've been sitting in front of one all day. It is, of course, the computer. Computers today can churn through trillions of calculations per second, and that gives them the power to do something very special. They can simulate evolution. More precisely, computers can use the principles of evolution to shape and refine their own programs, in the same way the natural world uses evolution to shape and refine living organisms. And today, computer scientists find that this evolved software can solve problems that would be beyond the smartest of humans.
One thing that we found, and particularly in our original research, is how powerful evolution is as a system, as an algorithm to create something that is very complex and to create something that's very adaptive.
Torsten and his team's goal was nothing less than to use computerized evolution to create a virtual brain that would control a virtual body. To begin with, they created 100 random brains. As you can see, they weren't up to much. Evolution then took over. The computer selected the brains that were slightly better at moving their bodies and got them to breed.
The algorithm then takes those individuals that do the best and it allows them to create offspring.
The best movers of the next generation were then bred together, and so on and on. Amazingly, after just 10 generations, although they're still a bit unsteady, the figures could walk.
Eventually, miraculously, you actually end up with something that works. The slightly scary thing is you don't know why it works and how it works. You look at that brain and you have no idea actually what's going on because evolution has optimized it automatically.
In 20 generations, evolution had turned this into this. But these evolved computer beings soon went far beyond just walking. They evolved to do things that really are impossible to program conventionally. They react realistically to unexpected events, like being hit or falling over.
Even though we program these algorithms, what actually then happens when it unfolds live, we don't control anymore, and things happen that we never expected. And it's quite a funny feeling that you create these algorithms, but then they do their own thing.
An unthinking process of evolutionary trial and error has created these virtual creatures that can move and react in real time. What we're seeing here is fantastic experimental evidence for the creative power of systems based on simple rules. Watching how computers can unconsciously evolve programs to do things that no human could consciously program is a fantastic example of the power of self-organization. It demonstrates that evolution is itself just like the other systems we've encountered. One based on simple rules and feedback, from which complexity spontaneously emerges. Think about it. The simple rule is that the organism must replicate, with a few random mutations now and again. The feedback comes from the environment, which favors the mutations that are best suited to it. the result is ever-increasing complexity, produced without thought or design. And that's the essence of this story. Unthinking, simple rules have the power to create amazingly complex systems without any conscious thought. In that sense, these computer beings are self-organized systems, just like the one Belousov observed happening in his chemicals, just like the ones in sand dunes and the Mandelbrot set, in our lungs, our hearts, in weather, and in the geography of our planet. Design does not need an active, interfering designer. It's an inherent part of the universe.
One of the things that makes people so uncomfortable about this idea of, if you will, spontaneous pattern formation is that somehow or other you don't need a creator. But perhaps a really clever designer, what he would do is to kind of treat the universe like a giant simulation where you set some initial condition and just let the whole thing spontaneously happen in all of its wonder and all of its beauty.
So what is the ultimate lesson we can take from all this? Well, it's that all the complexity of the universe, all its infinite richness, emerges from mindless, simple rules, repeated over and over again. But remember, powerful though this process is, it's also inherently unpredictable. So although I can confidently tell you that the future will be amazing, I can also say with scientific certainty that I have no idea what it holds.